Hello, welcome to Einstein Mechanics channel. We are treating strength of materials 1, and below are our course contents. In this tutorial, I'm going to take you through simple stress and strain. In other episodes, I will also take you through axial loaded bars or springs, then also temperature and shear stress. I will also do a video on centroids, moment of inertia, torsion, and bending. Today, our main focus will be on simple stress and strain. Simple stress and strain. Objectives. By the end of this tutorial, you should be able to describe stress and strain. Then also you will have a complete understanding what tension and compression in structures means. I will take my time to take you through that. I will also discuss tensile tests. We'll go through a lot of them. It is interesting. I will talk about factor of safety and then Hooke's law. At the end of each tutorial, there will be solved examples for each of the content. So in this tutorial, I will have to solve on simple stress and strain. There are problems we have to go through. So introduction, strength of a material. As engineers or as people trying to use material, we should know the behaviors of material, mostly the internal stresses. When I talk about internal stress, they are the internal forces acting in a material. They are very needed. Mostly those forces, the intensity of those forces determine the hardness, how the material is able to withstand forces and pressures. So it is good we know those things. So strength of material is basically giving us an idea of the internal forces in our structures or our materials. Remember, our main concern in this subject will be the internal effects of forces. The internal effects of forces. We will not consider if they are rigid or they are not. We will assume them to be rigid. So, stress and strain. Let's keep in mind this bar. Let's put our focus on this bar. I'm using it to explain a lot of things. Mostly people say, I am stressed. What does that mean? If you say I am stressed, meaning there's a force or there's a pressure you are going through which is unusual of your body, meaning something is going through you are not used to. So materials also get stressed. What does that mean? Meaning we induce a force in them which is greater or which is unusual of the material. Let's consider this prismatic bar. And straight away, when I say a prismatic bar, is a bar with the same cross section. You can see this bar. The width here, let's make it 4 millimeters, will be the same here. Also be 4 millimeters. And the length here should be the same length from here to here. Then we can consider this bar to be a prismatic bar. We are applying an axial force. What does it mean to say axial force? An axial force is a force which is acting at the length of the bar. You see, this is the bar, this is the length of the bar, and it is acting in the direction of the length of the bar, as we can see. Those are axial forces. So this bar is subjected to force P. The magnitude of this force is equal to this force. And we are trying to section this bar. What we are trying to do is to check the internal stresses inside the bar, because we cannot see them with our eyes. We have to make a section. We have to create, let's say, cut it with this A, section AA. We have to cut it and check the forces acting in the material to know the stress the material is going through. It is quite interesting. So when a section was made in this bar, we can refer from the previous slide. When this section was made, when we made a cut through this bar, this is what we got. We saw that this is force P, as we can see from P, and this one too is force P. So when this bar was cut, we saw that there are small magnitudes of forces acting in the opposite direction to this force inside. Remember, this bar was joining. This was the surface joining this place. But a cut was made and we saw some intensity of forces acting inside the bar. Let's assume this is force 1, F1, F2 to the last force, Fn. What we are trying to say is that this force P is equal in magnitude to the summation of F1 to the last force. So these are the internal stresses, the forces which were acting inside the bar we couldn't see. So stress basically is represented by this symbol, and stress is giving us the force over the area it is being considered. So if you want to find this stress amount of forces that was induced in this bar, we have to know the magnitude of this force and the area it is being applied. The area of the bar this force is being applied. So let's consider this bar. We can see that it was a rectangle. Therefore, the area was to be length. The length of the area was to be the length times the breadth. We can calculate it. Then we can use the magnitude of the force to know the stress. Maybe we have 4 kN force acting on a bar of length 2 meters and width 1 meter. Then we can finally know what it means. You can punch that with your calculator. So we should know the formula. Let's put in our head the formula for stress, internal stress or simple stress, which is represented this way: the force P over the area it is being applied. It is very, very important we keep the formula. It's very important. As we can see from here, uniform stress, the symbol was to show us what stress actually was. So stress P was the applied force and A the cross-sectional area, as we can see the formula here. The unit of stress is Newton meter square. Newton per meter square, or Pascal, simply Pascal, because let's deduce it. We know that it is equal to, stress is equal to force over area. We know the unit of force is Newton. Then area is also meter square. So basically stress is Newton meter. This will become a negative here. Or this is the same as a Pascal. So we can use that idea. Let's focus on compression and tension. From the beginning, I was talking about tension and compression. What does that mean? When a bar is in tension and when a bar is in compression, how do we know? You see, let's look at this force. acting on the bar. P. This bar is said to be in tension. Why? Because we can see that the force P is stretching the bar. It's stretching the bar. It is not compressing it, it is stretching. Therefore, there will be tension inside. It is trying to break. So there will be tension induced in this bar. So forces which are acting this way, we can say they are causing tensional effects or tensional stresses to our materials. And compression. What does it mean to say compression force? As the name goes, if a force P is this way, we can see from this diagram that the force is trying to compress this material, and as a result there will be also some forces induced in this material. Let's look at the difference. Let's get it clear. This is compression and this is tension. As we can see, what compression does is that it is trying to reduce the length. Check. As a material is compressed, the length here is trying to reduce, and tension is also trying to increase the length. Increase length. So mostly tensile stress is mostly positive. Why are we saying that? Tensile stress are mostly positive because there's an increase in the length, while compression or compressive stresses are considered negative because there's a reduction in the length. We'll solve most of the examples and we'll come across these things. So we should take good notes on this. It is very important we know about tension, strain. So let's look at what strain is about. I'll get my time and explain to you so that you get the concept behind strain. Strain is the measure of the deformation produced in the member by the load or the force. So let's assume our material of original length L is now being applied by an external force P. You see that the change in length to the original length, the ratio, is now the strain produced. It's very simple. So if I have a bar, let's assume this bar of original length L. Initially, this bar is not being acted upon by any external force. So it has its original length L. Then I apply a tensile force P to it. The tensile force P. I have my P. Remember, this force will try to pull apart this structure, causing an elongation. The length will never be the same. It will elongate my structure. So from here to here is my L. But when the force is applied, it will try to pull this through this distance, and I'll call that as my elongation. So there will be a slight increase in the length from here to this place. So now the total length of the bar is now L. That's the initial length plus the elongation. So what strain is talking about is very simple. So to see the strain in a member, it is giving us the elongation produced over the original length. Remember, not the final length, but the initial or the original length. This is in the case of tensile strain. Let's look at compressive strain. I have my member. Yes, this is my member. It is being compressed by this force P. Initially, still I have my length L, but as the forces try to compress this bar, I'm going to have a reduced length. So the bar is going to reduce to this place, and the final length will now be this. So what I'm trying to say is that there have been a decrease in length. I will still call it this. There has been a decrease in the length of this whole bar, giving us a negative what? Strain. So I can say still for the compressive strain, I have it as the elongation or the change in length over the original length. So this is for the tension and this is for the compression. I can still deduce it further. So strain is given as change in length. So from here, the final length, the change in length will be, so I have change in length over original length, but change in length will be final length, which was the L plus the elongation. This was the final length because it is the distance from the starting point to where the elongation took place, minus final length minus initial length, which was L over the initial length. So this L, we'll take this out, still giving us elongation over L. It's very simple. So now to the solved problems. Problem 1. A steel bar of rectangular cross-section 25 millimeters by 20 millimeters carries an axial tensile load of 3 kilonewtons. Estimate the average tensile stress in the cross section. So we have a rectangular bar that has 25 by 20 millimeters and the force. So solution. So let's assume this is the bar. The cross section area we can have here 25 millimeters by this. Remember, the area is the length times the width. So here will be 20 millimeters. We should convert units to meters. Remember, the unit for stress was Newton meter per second. So Newton meter per second square here. We should convert all our millimeters to meters. By the way, so we have the area to be 25 millimeters by 20 millimeters. Converting this to meter, you divide by 1000. This 2 by 1000. So I'm going to get the area to be 0.025 meters by 0.02 meters. And the area is going to give me 5 times 10 meters squared. So this is the area of the bar. The length times the width. Remember, it is a rectangle, a rectangular bar. We have the area. And the force, I told you in the other slide that the force can be the load. So this is the force. So I have the force F to be 3 kilonewton, which is the same as 3000 Newton. Remember your prefix. I can proceed and say that the average tensile stress given by this is giving us the force, or P, which is the force over the area. Now I have my force as 300 newtons and my area as 5 minus 4 meter square. Take your calculator and verify the answer. I am getting 6 megapascal. Remember, the unit for stress is or 6 mega Newton per meter square. You're going to get a huge value, but prefix it is mega. 6 times 10 raised to the power 6. So this is for the first example. It is very simple. You have to know your area. Says calculate average tensile stress. So let's assume the bar was in tensile stress. So the force was 3 kilonewtons. The tensile, so it was stretching the bar. 3 kilonewtons. So we want the stress induced in the bar, and we got it at 6 megapascal. That was a huge stress in the bar. You have your area. Remember to convert them to meters. You have them divided by 1000. That will give you this. So my area was 5 to the power negative 4 meter square. My force was 3 kilonewton, and that was 3000 newton. Stress is force over area. I have that, so I know my force, I know my area. If I punch everything, I'm getting 6 megapascal for example 1. Example 2. A steel boat 25 millimeter in diameter, remember the diameter, carries a load of 4 kilonewton in tension. Estimate the tensile stress of the section A and at the screw section B when the diameter of the thread is 20 millimeters. So here we have to pay attention here. You have to pay attention here. They gave us 2 diameters. First at section A. So I'm solving at section A. At section A, the diameter of the steel boat D was 25 millimeters. Remember, the same force was acting on the 20 millimeter boat or the section B. So we maintain the force F to be 4 kilonewton or 4000 newtons. We are to calculate or estimate tensile stress, but we know our formula for tensile stress to be the force over the area. At section A, where the diameter of the boat was 25, let's check the area at that place. But we have area, let's convert the diameter to meters. So I can say the diameter of 25 millimeters divided by 1000 will give me 0.025 meters. And the area, remember, a steel boat, we are assuming the boat was what? In a circular portion. You understand? So the force was acting at the circular portion of the boat. However the boat was, it was in a circular portion. So let's assume the top at the section A was a circle. So the area will be, the area connecting diameter will be pi d square on 4. So at section A, my pi times my diameter of 0.025 all square over 4. I'm getting the area to be equal to, let's have our calculators ready. I have it to be equal to 4.908 times 10 raised to the power negative 4 meter square for the area at the region 1. So I can calculate the stress now. So stress or tensile stress at region A should be equal to my force, which was 4000 newtons, on area of 4.908 meter square. So at section A, I'm getting my stress to be 8.148 mega Newton meter per second square, or I'm getting 8.148 mega Pascal. So this is the stress the force is inducing at the section A at a diameter of what? 25 millimeters. Are we good? So let's look at section B. Remember, the diameter of the section B was given as 20 millimeters. So now we are having a diameter at B to be 20 millimeters, which can be 0.02. Don't forget to send it to meters. 0.02 meters. Let's calculate the area. Remember, they will have different areas because the diameter differs, 25 and 20. So area at B will be the same formula, pi d square on 4, which is equal to, which implies that the area is equal to pi. The d now is 0.02 all square on 4. What answer are you getting for the area? I am getting 3.142 times 10 negative 4. Check different areas. I'm getting 4 point something here and 3 point something here. But the same force, I told you they gave us just a force acting at both section A and section B. So at section B, the stress, the tensile stress, is the same force over the area. The stress at B will be the 4,000 Newton force and the area of 3.142 times 10, 4. Good. So tensile stress at B is now going to be 12.730 mega Pascal, or 12.730 mega Newton meter square. The third example, example 1.3. A cylindrical block of concrete is 300 millimeter long and has a circular cross-section of 100 millimeters in diameter. It carries a total compressive load of 67 kilonewtons, and under this load contracts 0.2 millimeters. Estimate the compressive stress and the compressive strain. So in this example or problem, we are to estimate stress, compressive stress and compressive strain. From the question, we can see that the cylindrical block was under the influence of a compressive load. So the force was compressive. You understand? Let's write down our parameters. So our solution. Now, we can write down our parameters. A cylindrical block of concrete is 300 long. So the initial length of the block L was 300 millimeters. Let's convert to meters. We are getting 0.3 meters and has a circular cross section of 100 millimeter. So the cross section was 100 millimeter in diameter. So diameter D of the cylindrical block was 100 millimeters. So that would be 0.1 meters. It carries a total compressive load or compressive force of 67 kilonewton. So our force compressive was 67 kilonewton. And under this load, with this 67 kilonewton, the block contracts. We are talking about strain here, contracts 0.2 millimeters. So the contraction or the elongation, you remember this, is 0.2 millimeters, where we can convert to meters as 2 times 10 raised to the power -4 meters. We have everything here. What do we have to do? We have to estimate compressive stress, which is very simple. So I can say that my compressive stress will be my force over my area. I know my force, but I don't know my area. But I have the diameter here. So my area, since it was a cylindrical block but has a circular cross section. Remember, the cross section the force was acting was a circle. So we are using the formula pi d square on 4. So my area will be pi. What was the d? 0.1. 0.1 square on 4. What are we getting? I'm getting my area to be 7.8539 times 10 minus 3 meter square for the area. I can now calculate my compressive stress as the force was 67 kilonewton, which is times 10 raised to the power of +3, your prefix, over my area 7.8539 times 10 minus 3. This can cancel out. So I have Newton here, I have meter square here. At the end, I'm getting my compressive stress to be, what's your answer here? I'm getting 8.53 megapascal, or I'm getting 8.53 mega Newton meter square. So this is for the compressive stress. So in actual sense, it's supposed to be negative because it was compressive. So negative because it was compressing the block. But you can ignore the negative and still get your positive answer. You are right. Let's estimate the compressive strain. But we know that strain compressive is elongation over the original length. But from the question, we can see the elongation here. It contracts. Either it increases or contracts. We assume it to be the elongation, the change in the length. It's contract by 0.2. By the 0.2, we made it 2 times 10 -4 meters. The actual length, we got 0.3 meters. So now the compressive strain would now be 6.667 times 10 raised to the power -4. Remember, it has no unit. This will cancel out. Or we can still go by this. Compressive strain as the contraction over the original length, where the contraction, we can even use this straightforward. The 0.2, because the unit will cancel out, over the length. It was 300 millimeter long. You can still use the 300 millimeter. Remember, this will cancel out, giving us compressive strain of 6.667 times 10 raised to the power -4. No units. It's quite simple. So this is the solution to problem 1.3. Let's tackle the last problem under strain and stress. It's also very simple. We have to move at a fast rate. If we have any question, we can drop it in the comment section and we will attend to that problem. 1.4, the last example in this tutorial. A bar with a rectangular cross section 20 millimeters by 40 millimeters and length 2.8 meters is subjected to an axial tensile force of 70 kilonewton. The measured elongation, take notes, the measured elongation of the bar is even here, is 1.2 millimeters. Calculate the tensile stress and the strain in the bar. So we have a rectangular bar. Let's assume this is the rectangular bar. It has cross section. Let's take the length to be 40 millimeters by 20 millimeters. So we can have our area to be the length times the width. Let's have area length times width because it is rectangular, which is equal to 400 millimeters by 220 millimeters. We can divide by 1000 by 1000, which is equal to 0.04 meters by 0.02 meters. And the area I'm getting will be 8 times 10 raised to the power negative 4 meters square. That's for the area of the rectangular bar. We also have some parameters. So we have A equal to, we have the length which was given us 2.8 meters already. We also have the force, the tensile force, meaning it was in tension, it was stretching it, so there will be an elongation. The tensile force was 70 kilonewtons, and we have the elongation. Since it is tensile, it is going to elongate, but if it is compressive, it is going to contract. So the elongation was 1.2 millimeters, which we can also convert to meters as 1.2 times 10 raised to the power negative 3 meters. So let's calculate the tensile stress. It is very simple. So the tensile stress, T, tensile stress, the force over the area. From the question, we're having 70 kilonewton force, which is 70 times 10 raised to the power 3. On the area, we are getting 8 times 10 raised to the power negative 4. So we have newtons, we have meters square. So our final tensile stress is giving us 87.5 megapascal or 87.5 mega Newton meter square. That's for the tensile stress.